Hello, I'm Joshua Goldstein, an assistant research professor at the Social and Decision Analytics Division, part of the Biocomplexity Institute of the University of Virginia. I'll be speaking about the evaluation of broadband subsidy programs, combining spatial regression discontinuity designs and Bayesian wombling. This research is done in collaboration with John Pender at the USDA Economic Research Service and my colleagues from SDAT. Promoting rural broadband access is a high priority for rural people, Congress, and the administration. $1.8 billion in funding was allocated from 2018 to 2020 for rural broadband through the new Reconnect program. Several other USDA and FCC programs also promote rural broadband. More than $20 billion has already been invested by the federal government to promote rural broadband. An additional $20 billion is planned over 10 years through the new FCC Rural Digital Opportunity Fund. And the importance of broadband is even more evident in light of the COVID-19 pandemic. But despite of the importance of these programs, little research has investigated their impacts or their incidence. And so this research is aimed at investigating these impacts for specifically the USDA's rural broadband programs. This slide shows the funded service areas across multiple USDA broadband programs, including the Reconnect program, Broadband Initiatives Program, or BIP, Community Connect, Rural Broadband Loan and Loan Guarantees, and Telecommunications Infrastructure Loans. The initial focus of our research is on the impact of the Broadband Initiatives Program. We develop a novel methodology for comparing home prices for properties within and outside of USDA program boundaries. In addition to the program data given to us by the USDA Rural Utilities Service, we use CoreLogic data on property values and housing characteristics, and American Community Survey data on demographic variables to support this analysis. The goal is to develop models for property values using arm's length sales around the program boundary. To do this, we specify a hierarchical Bayesian spatial model. Our spatial domain of reference is a region that includes the program boundary and surrounding areas within 15 to 20 miles. We do predictive modeling of property prices around this boundary, accounting for spatial variation. And we do this by quantifying dependency introduced by properties located nearby or assumed to have similar prices. And we handle spatial autocorrelation at the point level as opposed to the areal or regional level, where points represent sites of houses where sales transactions have occurred. And using this, we produce an estimate of the variation across the spatial domain of reference and use this for interpolation at any location, also known as kriging. This slide shows the specification of our spatial model. Here, the response Y is the log housing price at a location S, and it's specified as a Gaussian random field with a vector of covariates X with coefficients beta, spatial effect, and random noise. Customary priors are specified here, and we use Gibbs sampling from the posterior, with the exception of the spatial range, which uses a metropolis within Gibbs sampler. To measure changes across the program boundary, we look at two different approaches: a spatial gradient assessment and regression discontinuity. To get estimates of the gradient at the boundary, we consider the joint normal distribution of the response and its gradient, and this leads us to a conditional normal specification for the gradient of Y. For the regression discontinuity approach, given a distance parameter C, we consider predictions from the hierarchical model within a distance C on either side of the boundary, and take the difference of these predictions across the boundary, giving us an estimate of the discontinuity across the line segment. So we compare the spatial surface of housing prices across the program boundary before and after program implementation. This plot on the left, pre-project, shows a simulation with random noise. And this plot on the right shows the same simulation post-project, where the program has had an impact raising house prices within the program boundary. For the gradient assessment approach, a steep gradient or sharp discontinuity in the surface is evidence of rapid change at the boundary of the program. So discontinuity in the gradients after a program implementation is evidence that the program is having an impact. This slide shows an example of a single program area in North Carolina. The project service area of this BIP program, the boundary is shown in light gray. Green points represent sales inside the boundary, and orange points represent sales outside of the boundary, along with the interpolated spatial surface of sales prices. Here's an example of another exploratory look at the same program data. Here we are plotting the log of sales price by distance from the BIP boundary. And the orange and green lines here show the median sales price outside and inside of the sales boundary. So here we can see that the median sale prices are higher pre-project, but this gap disappears when looking at post-project sales. Here's a summary of our model results across 7 different BIP regions. This is the estimated BIP impact comparing pre-2010 to post-2010 sales prices. And this impact is measured using the gradient assessment method as the % increase in house prices within to outside of the BIP region. This model controls for housing characteristics from CoreLogic housing data and sociodemographics from the American Community Survey. These program areas that we're plotting here are just a few of the many BIP program areas that we selected for having large numbers of sales and high loan amounts per household in the program area. In addition to these overall effects, we can look at localized analysis along the boundary. And this is done by measuring the value and direction of the gradient and its significance along each line segment across that boundary. And so that is what is being plotted here for the pre-project and post-project regions. We can see that red and orange gradients represent significant positive gradients across that boundary, whereas green and blue line segments across this boundary represent areas across the boundary where there are negative gradients. So pre-project, we see some significant disparities where we see these bolded lines which represent significant gradients at the boundary. However, these gradients become insignificant post-project, indicating that here locally is where this program is having an effect along this boundary. So the next steps for this research are to do a complete analysis of impacts of all BIP program areas on house sale values, and to look at the meta program effects, the impacts that different project types, different technologies and contexts have in terms of their impact on sales values. We would also like to look at the impacts of BIP on other outcomes, including business startups, migration of businesses and people, and employment growth of different race and ethnic groups. And in addition to the impacts of the BIP program, we are expanding this with other program data obtained from the Rural Utility Service, including the Reconnect and Community Connect programs on these same outcomes. And in the case of the Reconnect, we can look at these program outcomes before and during the pandemic. Thank you.